exponential models. As promised, I'm going to go back and review everything from the start of grade 11, but then throw some grade 12 stuff in there, throw some logs in there. Show you how questions were done in grade 11, then show you, okay, how has it changed in grade 12? To start that, I want to completely review what exponential models are and why they exist. So the first half of this lesson is mostly grade 11 stuff. So I made up this silly example. The number of cockroaches in Mr. Todd's house is 5, and that number doubles each week. How many cockroaches will there be in 10 weeks? When you first see this question for the first time in your life, this might be the way you want to do it. You say, okay, well, Mr. Todd in week 1 starts with 5 roaches. By the end of the week, that population is doubled to 10. Yes? Then the next week, it doubles to 20, then to 40, then to 80, then to 160, 320, 640, 1280. You just keep multiplying by 2s. And it's a decent method if we're only doing 10 weeks. But if we turned around and wanted to know how many cockroaches there'd be after 20 weeks, you might get bored with this method. So look back with how I wrote it. I wrote it and said, okay, after 1 week, it would be 5 times 2. After 2 weeks, it would be 5 times 2 squared. After 3 weeks, it would be 5 times 2 cubed. After 4 weeks, it would be 5 times 2 to the power of 4, because I just keep multiplying by an extra power of 2. And by writing it that way, instead of going to the final answer, I can create an exponential model. That's the whole deal about exponential models, is saying, okay, start with your 5, and then multiply by 2 however many weeks have passed. So you can imagine if you wanted to do how many cockroaches there was after 20 weeks, what you'd write down would be 5 times 2 times 2 times 2 times 2, 20 times, but exponents give us a much better shortcut, 5 times 2 to the power of 20, whatever that is. The point of this lesson is not to get that number and actually figure out how many cockroaches there are. It's to go, we do not have to use a table of values to do this. There's an exponential model which says, okay, this is the big thing about exponential models. Put the start value there and put the growth factor there. I'm hoping that rings a bell from grade 11. If it doesn't, it doesn't matter. I'm reteaching it right here. So we can now find a general model for these types of situations where the amount of something doubles, triples, quadruples, grows by 8%, shrinks by 9%, any situation like that. They're all called exponential situations, and they all have the same equation, a start value and a growth factor, and that's it. That's all there is to exponential equations. Does this ring a bell? All right. In fact, to really ring a bell, usually it's written like this in grade 11, but it does not have to be written like that. I'm going to show you a bunch of other ways to write it. So the model for exponential growth is y equals ca to the x, where a is greater than 1. Right now, I'm just focusing on exponential growth, not things that decay or get smaller, because then we need a different a value. And I'll get to that later in the lesson. For now, I'll just act like it has to grow. It has to double, it has to triple, something like that. So the quantity a can be called the growth factor, usually called the growth factor, and the quantity c is the initial amount. Very simple setup. You put the initial amount there, and you put the growth factor there. There's only a couple of things to remember here. The growth factor does not need to be a whole number. The previous example, I set it up to be doubling, and I knew the doubling time, so that a was a 2, but there's no reason for it to be a whole number. It can be any number greater than 1. Unless the situation is exponential decay, which I'll deal with in a minute. So if you're like, oh, wait, you can have things get smaller. I know, I'm going to get to those in a minute. So the cockroaches could have had a growth factor of 2.3 or 7.11 or something strange like root 7. Any growth factor is really possible. I just made, for my example, I just went and said, what I'm going to do is I'm going to make the cockroaches double, exactly double, every week. Well, what population actually does that? And the answer is money actually does that, because sometimes they give you your percentage of money at specific intervals. But cockroaches do not care about weeks, so there's no reason it should be double every week. And we may have to work backwards to find the growth factor or initial population. No, you would not have to in grade 11. This is what you didn't have to do in grade 11, is work backwards. All the information was given, and you just plugged it in. But today, because we have logs now, we'll be able to work backwards if we need to. We're not scared of that at all now. So here's an example, and I love this example because it does 2 steps of grade 11 and then shows you the difference between a grade 11 and a grade 12 question. So here we go. Grade 11. A certain bacteria triples every hour. If there are 30 bacteria initially, find the exponential model. So the exponential model would be number of bacteria would be equal to initially 30, but now tripling every hour. So I'm just going to put T. T is number of hours. That's as simple as setting up exponential models is. You put the initial value right here, and then you put the growth factor here, which apparently the question will tell us something about the situation and tell us what growth factor to use. Do bacteria triple every hour? No, I can't imagine that bacteria care about your watch at all. So I just put that up there just as a basic example to start off with. And then what would you do in grade 11? Then they tell you find the population after 7 hours. So you'd go B equals 30 times 3 to the power of 7, and you'd hammer that into your calculator, and you'd get the answer. Get mine out. 30 times 3 to the exponent 7. 65,610. End of grade 11. That's what you did in grade 11. Okay? In grade 12, now, we can ask this question, which we couldn't ask in grade 11. When will the population be 1,000 bacteria? We want B to be 1,000. When will we reach that threshold of 1,000 bacteria? So instead of substituting in the T, we're substituting in the B. I want to pause there and really highlight why we could not do this in grade 11. There was no way to solve for a variable that's up in the exponent like that. But we can do it now. Yeah? Isolate the exponential part. 1,000 over 30 equals 3 to the exponent t. You could get this as a decimal. I don't suggest it. With your guys' calculators nowadays, there's no reason to do anything here. You might want to simplify it. So I will do that much. I'll go, okay, I can simplify that to 100 over 3. But I wouldn't go any farther with it. I wouldn't get it as a decimal. I'd just leave it like that. And now I got to reteach Thursday and Friday's lesson. When there's an unknown on the exponent, log both sides. Those of you who have the fancy calculator, I'll show your method in green off to the side here. If you don't have the fancy calculator, you just put log on both sides. And the reason we do that, to completely review Thursday and Friday, and maybe the whole chapter is, now when I have log on both sides, that unknown in the exponent can come down as a multiplier. And now it's not an exponent anymore, it's a multiplier, and now I can just divide to get t. T equals log 100 over 3 divided by log 3. And by log, I mean common log, the regular log button. See, the calculator I'm holding up here today is just one of these. It doesn't have the fancy log button, so I can just type it right into there by typing in, oh, can I even find the log button on here? Log, open bracket, 100 divided by 3, close the bracket, divided by log 3. I get 3.19. And some other decimal places, 1806549. Does anyone else get that when they type it in? Now's a good time to practice typing these in. Now I'm going to put that calculator down, and I'm going to get out my fancy one. It doesn't have to be this fancy. And I'm going to do this the way some of you could do it with your fancy log calculator, is you'll go 3 to the exponent, moves over and becomes log base 3 of 100 over 3. And just type that into your calculator. And now I got to find my fancy log button on this calculator. And I go log 3 of 100 over 3. And I get 3.19. I'm less than surprised. Well, approximately 3.19. You know, like it's rounded off. someone raised their hand and go, I like this thinking. I like 3 to the power of moves over to become log base 3. And after the trick you showed us last week, can't I just do that then? I don't have to do log of both sides. Can't I just do log base 3 of 100 over 3, and then to type it in my calculator, I go log 100 over 3 over log 3, and the answer is absolutely. That is another way to go about this question. So there's actually 3 ways to go about this question. What questions do you have on that? It's taught after that whole chapter. 3 to the power of moves over and becomes log base 3. That's the whole story? The answer is, yeah, actually. Sort of weird, right? Seemed complicated as it was going through, and it was complicated because it was very new. But there's this moment where you break through on all this stuff. Okay, that's a bacteria question. That's for you biology people out there. That's where you use logs in biology. Like all the time, but not difficult. You know? More time there? Okay, a financial one for you business, economics type people. A very simple one. I'm not trying to solve all the business economics questions in the world here, but here it is for business people. A vintage comic book is worth $500. It's increasing in its value at 15% per year. Find the exponential model. So the value of this comic has a start amount of 500, and then some growth factor. T is now in years. But we need somebody right on the case to help me with the growth factor. If you're growing by 5% per year, what do you multiply the value by every year? 1.15. Does that ring a bell from grade 11? It's awfully tempting to go 0.15 here, but that's not going to make it grow. 0.15 is going to find 15% of it. We want to have 15% more than what the value is. If you want, you're using 115% as your growth factor here. Multiply it by 1.15 every year. So there's the exponential model. And here's the end of grade 11 right here. Find the value after 10 years. You just go 100 times 1.15 to the 10. And you get your calculator out. And you go 500 times 1.15 exponent 10. This comic will be worth $2,022.78 in 10 years. There's the end of grade 11. A question you couldn't ask in grade 11. Find when the comic will be worth exactly $2,000. Now we get 2,000 equals 500 times 1.15 to the exponent t. And here's Thursday's lesson in a nutshell. Isolate the exponential part. Then because, and I'm going to say it over and over again, then because the unknowns in the exponent take common logs of both sides. And the reason we do common logs of both sides is because it allows that variable up in the exponent to become a multiplier instead. Log law 3 allows you to move that down out front. And then I can isolate t. And type that into any calculator with a log button. And it's 9.9 years. Now, where's the steps for you fancy calculator people? You'd probably, here you'd go log base 1.15 of 4, and then you jump right to there. Yeah? I like both methods. If I've seemed like I'm trying to do a sales pitch for one method over the other, I'm trying not to. I'm trying to say, yeah, either way will do. Any questions on that? So all log did was change this question so that we could do it in reverse if we wanted to. We could back this out. We could do the other way of solving here. That is, if they gave us the t in grade 11, we could get the value of the comic. Now, if they give us the value, we can get the t. That's what logs allows us to do. More time there? As promised, a reverse example. That is an example where the value's depreciating. Find the value, find the exponential model. Mr. Todd's van is worth 20,000 and is depreciating at a rate of 20% per year. I wish the depreciation was only that much. Actually, this has all been messed up by coronavirus. Values of cars have actually depreciated less than all this because there's less cars around. And anyways, doesn't matter. I'm not going to sell my van anyways. Value equals. Always the start value right there. That's what's beautiful about exponential models. You always put the start value right there, 20,000. And then there's some growth rate per year. T in years here. This one's, no, I don't know if it's hard. You got to think about this for a second though. If my van's depreciating at 20% per year, what am I going to be multiplying the value by every year? 80%. I like how you said that. And I'm going to write it like that. I'm going to write 0.80 because if I had wrote 0.8 there, maybe I would have confused somebody. But 0.80 because I want 80% of it. It's decreasing by 20% every year. That's the only new thing in this question. The rest of it's like identical to the previous question. If I want to know the value of my van after 10 years, I just put a 10 in there for the T, 20,000 times 0.8 to the power of 10, $2,147.48. You know, I'm crying like I care. I don't care what my van's worth. I'm going to drive it until the engine falls out of it. So what do I care what the thing's worth? You know, I don't care how long it's going to last. There's grade 11. Make the exponential model, plug in the time. Here's what you can do this year. You can find out when the van will be worth $1,000 by plugging in the 1,000 on the other side. The unknown's up in the exponent, so isolate the exponential part so that you can take logs of both sides. Allowing you to bring that exponent down. And I said it fast that time on purpose, not to rush the lesson, but to get that point across, is that when there's an unknown in the exponent, do logs of both sides so you can bring it down. That sentence hopefully is starting to become simpler to think about. And that allows me to use division to find this T instead. Get my calculator out. Log of 1 divided by 20 divided by log of 0.8, 13.4 years before my van is down to $1,000. Oh yeah, where's those steps for you people who want to use your calculator? You're going to write here. You're going to write log base 0.8 of 1/20th equals T, and then you're going to jump right to there, to the final answer. I'm okay with both methods. He said again. I keep saying that. Any questions there? Is this mostly coming back to you? Not part C. Part C is I taught you last Thursday. But the first two parts, the exponential models, I don't know how much time they had this year to do exponential models. Sometimes it gets rushed at the end because it's perceived to be the easiest thing you do in grade 11. I don't know if it is the easiest thing, but it's perceived that way. And so sometimes other things take up all your time and you don't get much of this. And that's why I've added on to this lesson to make sure it's very clear what's going on. More time? So here's the review of that. I just slid that in there and showed exponential decay. The general model for exponential decay is y equals c(a) to the x. It's the exact same thing, except the a value's now got to be some kind of decimal or fraction to make things smaller. So when you're doing exponential decay, that number is going to be smaller than 1. sometimes called the decay factor. So the only difference here is the growth factor will be a fraction or a decimal, and the population will be getting smaller. So if you get a question where the quantities are getting smaller, look for a decay factor between 0 and 1. I'm going to lay the highlighter on that one because I think that's key in these decay questions. If things are getting smaller, look for a decay factor, decay factor between 0 and 1. Exactly the same as the previous examples, except it has to be between 0 and 1. Special examples with special versions of the model. What? Another bacteria doubles every 2 hours. See, the bacteria aren't going to care about your clock. They're not going to double on your schedule. So this actually, even though it says doubles every 2 hours, this example will help you do any doubling period you want. I'm going to show 2 different ways to do this thing. You could do it the old way. You could go y equals c a to the x. But now the x is the number of doubles. How many times this thing's doubled? So we're going to think a little bit to use this model. This is the thinking version. This is maybe the math version. The math people will just go, no problem. I just figured out how many times it doubles when I go to do this. So they would do this and they say, okay, the initial population is 50. Growth factor is 2. There's my model. And here's the big moment. After 10 hours, y equals 50 times 2 to the think. How many times has this thing doubled? It doubles every 2 hours. 10 hours have gone. I'm making it like you got to think a lot here. You don't actually have to think a lot. Some people are doubting their thoughts now. They're like, why is he making this out to be such a big deal? How many times has it doubled? 2 hours, 10 hours? 10, I like what he said there. 10 divided by 2. So there's a fraction up in the exponent because it's only doubled 5 times. I hope you see the danger of this. It's a dangerous way to do this because it would be easy to forget because all the other questions, the exponent was the time. And so it would be easy to just plug in 10 there and not know the number of doubles. So scientists, mostly, there's other people who use this formula, have come up with what's called the doubling formula. And this is the other way to do this. It's the safer way to do it. It's the less thinking way to do it. We say the number is equal to the initial amount times 2, but then they actually put in the formula t divided by d, which is this is the doubling time. So they actually build it right into the formula. It's the same formula. It's the exact same. This big A is for amount. The scientists go, no, we're not going to call that C anymore. We'll call that A for amount. And we already know it's doubling, so we'll put a 2 right in there because we know this is a doubling situation. So when you see the word double, it can be convenient to jump right to the doubling formula. And in the doubling formula, you go, okay, the number is initial amount, which is 50, times 2 to the t over the doubling time, which is 2. Do you see how that's safer? The formula actually tells you, don't forget to divide by 2. Maybe you're unimpressed by this formula. Hopefully I've taught it in just a way that you're unimpressed by this formula. So you're just going to put the 2 in there for doubling already, and you're just going to remind yourself to divide by how long it takes to double, and that's exactly what this thing does. And so what I get is here's 50 times 2 to the 10 over 2. The good news is that's actually hours now. You actually put the hours in, and you'll get the same answer here. And again, I'm not doing a sales pitch for either, but I do know if you're going into sciences, they're going to use the doubling formula lots. They love the doubling formula because it's sort of low maintenance. It also allows you to go, oh, it doubles every 11 hours, or it doubles every 2.7 hours, or it doesn't matter how much time. You just put that in there, and it solves all of that problem too. You don't need your bacteria to be well behaved and have little watches on and go, oh no, don't double yet. We only get to double every 2 hours. No, the bacteria aren't going to do that. They're going to do whatever they feel like. And this prepares for that. There's also a half-life one. Looks exactly the same. Here's the two formulas. N equals initial amount 2 to the T over D. And then the half-life one is N equals A 1/2 T over H, where H is the half-life. So D is the doubling time. T is, sorry, and then over here, H is half-life. Which, if you've never seen the word half-life before, I'm going to do a little speech on half-life in just a second. So you get to hear all about half-life in just a second. But these are low-maintenance, science-type formulas which remind you the right things to do. They're sort of lower maintenance, lower thinking. Let's talk about half-life for a second. When they find a dinosaur bone, they know very specifically how much carbon is in a dinosaur bone when the dinosaur dies. And let's just imagine for our examples that we know there should be 100 grams of carbon in there. Carbon decays at a very specific rate. Very, very specific. Shockingly accurate this is. So if they look at a dinosaur bone and half of that carbon is gone, they know 5,730 years have passed. And you're like, well, what if it's buried in stone? What if it's rained a lot? Yeah, they can factor all that in by the quality of the stone around the bone. So then what they can do is take a dinosaur bone and do the exact calculation we're going to do here, and then find out how old this dinosaur bone is. And this is how they fill in the evolutionary chart, is by going, oh, this bone was this old, this bone was this old, so this animal turned into that animal, and away you go, over thousands and thousands of years. I mean, long time, like millions of years have passed, and that allows all of this process to carry on. Well, without getting sidetracked by all the science, I'll give you a different example. The half-life of my paycheck is about a day. There's a reason for that. That money comes in, and I've scheduled a whole bunch of bill payments to come out the day my paycheck comes in. I don't want them to come the day before my paycheck comes. So my car payment, my insurance, a whole bunch of stuff comes out right away. So half of my money is like gone in the first day. Then after that, we got to slow down if this pay is going to last. So the half-life of my paycheck, you could think of it as a day. It takes half of it appears in a day, and then I'm like, oh, we got to slow down. Then another half disappears, and another half disappears. So, like for instance, go back to my carbon example here. If a bone has 100 grams of carbon in there, after 5,730 years, it goes down to 50. 100 years later, it's down to 25. 100 years down to 12.5. It's always going in halves. So here's my example. The half-life of carbo. Did I fix this in your note? The half-life of carbon. My note has a mistake in it. Carbon is 5,730 years. It is known that a certain dinosaur bone will start with 4,000 milligrams of carbon. How long will it take for the amount of carbon to reduce to 500 grams? So this is exactly it. We know that a certain dinosaur bone should have 4,000 milligrams when it dies. We found a dinosaur bone that only has 500 grams of carbon. We want to know how much time has passed. So here we go. Half-life formula. N equals A 1/2 T over the half-life. I'm telling you, this is the exact same equation we've been using. We have an initial amount. We have a growth factor, but they told us what the growth factor was. They said it was half-life, so we know the growth factor is 1/2. But we have to divide by how much time has, how many half-lives have happened there. Let me plug it in to show you. We know we're down to 500 milligrams. The initial amount was 4,000 milligrams. I'm changing that to a 0.5. You don't have to. You can type in 1 divided by 2, but I don't know, most people like typing in 0.5 instead. And then this is T over 5,730. And if you're confused by the T over 5,730, don't worry. In the steps I take to solve this, we're going to talk about the T over 5,730. Okay, the unknown's up in the exponent, and it looks a little complicated, but it's up in the exponent. So we want to do logs, which means isolate the exponential part. And I'm going to go to all decimals here. In this particular question, you don't have to go to decimals, but this is 0.125 equals 0.5 t to the 50 over 5730. And now I do that move. Log both sides. Because logging both sides allows that multiplier out front to come down. Sorry, that exponent to come down as a multiplier. And I'm going to skip, I'm going to not do a step here because I want to talk about what I've got here. I'm going to do that much and punch it in my calculator. Log 0.125 divided by log 0.5. And I get 3. There's no reason it should have came out to 3, except I rigged it up for teaching purposes. What's happened is the amount of carbon has gone in half 3 times. It went from 4,000 down to 2,000, then down to 1,000, then down to 500. There's been 3 half-lives in there. And that's why the divided by 5730 has to be there. It would be awfully tempting to answer this question and go, oh, 3. 3 years have passed. Since the dinosaur died? 3 years have passed? No, 3 half-lives have passed. So I've got to take that 3 and multiply it by 5,730 to find out the actual time. And this is still a ridiculous example, by the way. We don't find bones that are 17,000 years old too often. Usually they're tens of thousands or millions of years old. You know what I mean? But I wanted it to be very simple the first time you're through. 17,190 years old these dinosaur bones are. Any questions about half-life questions? The formula is one you'll need to memorize. He said not sure whether he'll make you memorize it for the test or not. But in theory, you want to memorize these formulas. But they're not that complicated. Like initial amount, half-life formula with a half in there. And you just got to remember to divide by the half-life because that exponent has to be number of times this thing has gone in half. Questions there? Okay, compound interest. This you're supposed to do a whack of in grade 11. Like you're really supposed to nail this down in grade 11. But I think sometimes it gets forgotten. Like you sort of cram it into your brain and then you forget about it. So the compound interest formula is A equals P times 1 plus I to the n. And here's some important things. The P is the principal, which is the initial amount. And if you're like, here we go, another formula. I hope I'm going to teach this in such a way that you go, this is not a new formula. We've already used this formula once today. I is the interest rate per period, and n is number of periods. So a simple example, then a complicated one. Mr. Todd invests $1,000 at 5% per year for 10 years. Find the final amount. Straight out of grade 11. A equals 1,000 times 1.05 to the n. And I did it just that way to prove that this is the same formula we were using before. I used this exact formula not called compound interest when I did the comic one. You see? Initial amount, growth factor, t. Done. So compound interest is the same thing. The only difference is they put this 1 plus I in there to remind people if it's 15%, you got to add that onto 1. 1.15. So it's like compound interest for dummies, basically. You know, if you don't know what's going on, take 1 and add the interest rate. Here was 5%. Oh, I didn't need an n there, did I? I was getting ready for the second question. I know the n. It's 10. So my $1,000, if I leave it in the bank for 5 years, or sorry, for 10 years at 5%, after 10 years, now I'll have $1,628.89. Does that ring a bell? Did you do compound interest in grade 11? No, you didn't. You skipped over it. Well, okay. I'm trying to teach it in such a way that this formula does not seem mysterious at all. It's like it's the formula we were already using, broken into little pieces so people can handle it. However, there's a problem with compound interest. And I got to tell you a story first to motivate the problem. Let's imagine for a second that I give my daughter $12 on her birthday every year. Boy, do I wish I could get out for $12. That would be great if birthdays only cost me $12. That would be fabulous. But just for the example, just imagine I give her $12 every year on her birthday. And she decides, Dad, I really like birthdays. I really enjoy the cake. I really enjoy singing. I'd like to have a birthday every month. My birthday's on the 4th. I'd like to have a birthday every month on the 4th. To which I go, yeah, that's pretty good. That's pretty fun. I like the idea. All right? Good. Her birthday comes. First time the 4th comes up, she says, okay, here we go. Where's my $12? And I'm like, no, you're not getting $12 every time. You're still getting $12 for the year, but you're going to get $1 each month that you do this. Then you get $12 for the year. Does that make sense? All right, check out this example. Mr. Todd invests $1,000 at 12% per year, compounded monthly. How long until he has $4,000? I got big plans for this money. I need $4,000. I'm going to invest $1,000. This is going to take a long time to get to $4,000. Same formula. A equals P times 1 plus I to the n. I want to end up with $4,000. That's a dream. Start with $1,000. And this is 1.01, and I need somebody who's right with me to explain why it's 1.01. Chloe. Yeah, you can compound monthly, and this makes a lot of sense. People don't want to wait to the end of the year to get all their money. They want to get some of it, just in case I want to take it out, pay some bills, do whatever. So lots of things are compounded monthly. You get your interest monthly, but you don't get the 12%. You get 1% per month. And actually, doing it this way, you end up with more money than you would get normally, because your interest gains interest a little bit. You know, you put the 1% in there, and then it adds on to that, and away you go. That's the first situation with this. When it says compounded monthly, and they might say compounded quarterly, they might say compounded semi-annually. You'll have to divide by however many compounds there are. The rest of it seems pretty straightforward. Isolate the exponential part, log of both sides. I'm doing that fairly quickly, not because I think that that should be easy at this point, but because it's not the point of what's about to happen here. I want to get to the answer. 139? 139? 139 years? It's not right. That's not right. It's not 139 years. 139 months. This formula calculates how many periods have gone by. We were doing compounded monthly, so that's the number of months. That's the other quirk with the compound interest formula, is your n isn't years. And I put that up in the thing here. It says n is the number of periods. You can see it right at the top of the page there. And the number of periods here, they were monthly periods we were doing here. It was monthly you were getting interest, so that final answer is in months, not years. How many people remember seeing compound interest formula in grade 11? No, it sometimes gets skipped over. But I try to teach it in such a way that it's really the same thing as regular exponential growth. Okay? It might have already been in a homework question. You might be like, what am I supposed to do here? Now you know. And then you can go back and do those homework questions. Because, like I say, you're supposed to in grade 11. All right. That part we actually don't usually teach in advanced functions because usually you cover a lot of that in grade 11, and to do the log part of it was no big deal. Here's the actual grade 12 lesson now. The actual grade 12 lesson is called Creating Logarithmic Models. And there's a lot to it. It's a long written thing there, and we don't need to do all this. I just want to talk about one thing. The piano doesn't do what you think it does. That is, when you go from here to here on the piano and play a note that sounds the same, but just in a higher octave, it's actually doubled the frequency. And then you've doubled the frequency here. But they don't space it out like that, you see? Like this is 128 times the frequency, but it's only like this far away. Like if they built pianos linear, a piano would be like as wide as your house. To get to the highest frequency, you'd have to run down all the way to the other end of your house to hit the key that had 128 times the frequency. So they don't build it like that. They build it in a log scale, basically, is what they do. They double every so often. So that's what we mean by logarithmic scales. Now, you don't need to know that. That's not what you need to know from this note. And you can read that over you want. I included it because it's interesting reading for music people. Here's the part I want to talk about. Earthquakes is the part I want to examine here. Hi there. Welcome.
Sorry if this is a bad time, I can come back at lunch, but I'm doing an art project and I need like a bunch of textbooks. Do you have any that I can,
How many did you need?
just like 5 or 6.
Do they have to be in great shape or no?
No. Indeed.
There's 6 that are sort of beat up.
Okay, that's perfect. And I can write down all the numbers.
Sounds good. Okay, let's talk about earthquakes for a second. Earthquakes are dramatically violent. And let's just talk about what an earthquake does for a second. And if you're blown away by how much there is left in this note, there's shockingly little left in this note. I'm going to tell big stories about earthquakes, but there's shockingly little to know about what's actually going on with earthquakes. But what I'll tell you is, we don't know much about earthquakes here. In my whole life, I've only ever felt one earthquake. I was down in the basement of a parent's house playing Nintendo 64. I can remember it clearly. And this is how long ago this was. My TV had rabbit ears on it. Do you know what rabbit ears are? Just 2 antennas sticking up in the air like this, yeah? And I looked up and the antenna started doing this and I was like, I heard like a rumble. Sort of, I thought there was a big truck going by. So I went outside to see what the big truck was. There was no big truck. The earth was moving. This is freaky where we live. We're shocked by this when the earth actually moves around like that. I think later they said that the earthquake we had in this area, which are very rare, which was around a 3.7. That is, most people didn't even feel it. Okay? Now, from a 3.7 to like a 4.7 is an earthquake that is 10 times as much energy. So this scale that goes up nicely, see, it's such a nice scale. 1, 2, 3, 4, 5, 6, 7, 8, 9. Seems so nice. But each of these moving up one is a power of 10. That is, when you go from 5 to 6, that's 10 times the energy released. So when they say, okay, this earthquake was 6.5, did major damage, people died. Then they say 7.5, you're like, oh, okay. Doesn't sound too bad, right? 6.5, 7.5. It's 10 times worse. Yeah? So those numbers start to mean a really big deal. Well, normally 6.5 to 7.5 isn't much. Well, you think about a hockey game. 8 to 7 in a hockey game is really close. 8 to 7 in earthquakes is not really close. That's 10 times worse. That's the end of my speech on earthquakes, actually. If you want to do an earthquake question, and there's a bunch of stuff in earthquakes here, is how they find the Richter magnitude. And they listed a bunch of famous earthquakes, if you care about these famous earthquakes, and how devastating they were. But to give an idea, one of the worst earthquakes in history, just totally devastated the whole area of Chile, was a 9. If we went to a 10, that would crack the whole Earth in half, because it would be 10 times more devastating. We're not about to have these things. I'm just saying that 9 to 10, oh, it's a 10 versus 9. No, that's a really big deal. Here's the type of questions you're responsible for. How many more times intense to the nearest whole number was the 1995 earthquake in Japan, which was a 7, versus the Little Skull Mountain, Nevada one, which was a 1.5, and here's the answer right here. 10 to the 1.5. You see, the Richters were 7 minus 5.5. It's only 1.5 more. You're like, oh, that's not so bad. 5.5 versus 7. No, it's 10 to the 1.5 more. 31 times as intense. So the difference on a Richter scale between two earthquakes is actually an exponent, a difference in exponents. Let's do one more. According to the table, a tornado that goes through usually has an average Richter scale magnitude of 4.5. That's how much energy it releases. And it says, how much more intense is the San Francisco, a famous earthquake in 1906 that was an 8? Well, 4.5 to 8, 3.5. It was 3.5 more. No, it was 10 to the 3.5 more, which is 3,162 times as intense. Let me say it again. The difference in Richter magnitudes is a difference in exponent tens. So you put the difference on exponent 10. That's as simple as getting through the Richter scale is. What does that have to do with logs? Well, that's where it all comes from. The intensity is a log of the Richter scale magnitude. Decibels works very, very similar. Except, actually, I don't know. What I'm going to say next is speculation. This may not be true. Scientists decided to make a scale that was about 1 to 10 for earthquakes, because that was easy to reference. You know, like 1 to 10. 10 being one that would probably destroy the Earth. 1 being one that you could barely feel unless you were close to it. It's a good scale. The sound people with, have you ever heard of decibels? Decibels of sound? Yep, okay. They did it similar, but they wanted the scale to go from about 1 to 100, so they multiplied the whole thing by 10. So the whole thing is multiplied by 10. Barely able to hear sound is like a 0, and a boiler factory, which would damage your ears, unbelievably loud. The loudest any human would want to be anywhere near, still probably do damage to your ears, would be like 100. So they took the whole scale and multiplied it by 100. What does that mean for doing calculations? Right here. I don't want you to do this. I want you to do this. The difference in loudness of two sounds is 7.2. So how many times louder is a music concert of 125 decibels than a conversation of 53? So the conversation between us right now, I might be speaking at about 53 decibels. If you went to a concert, one of those ones that when you leave, your ears are ringing the next day. Have you ever gone to something like this? Where the next day, literally all day, your ears ring? The difference would be 73. So the actual, let me just write it out here. 125 decibels, subtract 53 decibels, is 72 decibels. 72 decibels difference, and so that's a difference of intensity of 10 to the 7.2. So they multiplied the whole scale by 10. And so that's 15.8 million times the energy. So with Richter scale, it's a difference in exponents. With decibels, it's a difference in exponents, but it's been multiplied by 10. You've got to divide by 10 before you actually use it. Why did they choose these things? I'm not exactly sure why. I do know why they chose difference in exponents. because you don't want to be talking about things that are 15.8 million times as intense. You want to put a nice friendly number on it. 72. Yeah? It makes it easier to manage. The last one is the one I really care about, which is pH. We're the chemistry people. Yeah? Chemistry, this is going to come up. pH is negative log concentration. And the reason it's like that is because it's unbelievable how much difference in concentration you can get. This comes up in your pool, right? You want to get the right pH in your pool. And the difference in pH, like if you go from 6 to 7 in pH, it's like, oh, it's just 6 to 7. No, that's 10 times more concentration of H plus ions. So here's the formula for finding pH. It's negative log concentration. So if they give you the concentration, you can just plug it in and do negative log of 0.0001, the concentration, and I get 4. Here's another concentration, look at how much more concentration this is. 0.0001, 0.0022. This is way more concentration, but the pHs are only 4 to 2.66. So this is a difference in the exponent on 10, so it's the exact same thing as what we were looking at with the decibels and the Richter magnitude. Mr. Todd, do a reverse example here. Find the pH. Find the pH if the H plus concentration chemistry people, do you guys do little square brackets for concentration? Doing that yet? Yeah, okay. If the H, I'm not going to say that. I'm going to just say if the H plus concentration, if the amount of H plus concentration ions is, I'll do one that's close to these, 0.0001. Well, they already did 0.001. I'll do 0.0015. So pH is negative log. Oh no, I want to do it the other way. Oh, the whole point was to do reverse example. Oh, I'm so sorry if you copied that down. The whole point was to do a reverse example. Find the H plus concentration of pH equal to 8. I'm going to do a massive difference in pH. So here we get pH equals negative log concentration of H plus. And again, if you're in chemistry class, you probably just put that in the square brackets. This time they gave me the pH. And you can see why. Look how not fun it is to write concentration of H plus every time. How am I going to get that concentration? I'm going to write it like a chemist here. 8 equals negative log H plus. Well, first I move the negative over. And then I got to move the log over. About to wrap up the chapter, folks. Log's coming to an end right here. Oh, I hope we know. How do I move that log over? First of all, what base is it? 10. So I know that's base 10. What happens to it when I move log base 10 over? (10 to the exponent negative 8 will give me the H plus concentration, which I don't think my calculator is going to do anything fun with that. Yeah. Done. There's a homework question like that, right? Any questions on those? I tried to do the second half quicker because all you needed out of that second half was pH, decibels, and Richter scale. And they're all pretty straightforward to actually do. They all have straightforward steps to do.